These are the definitions to acids and bases. So, first of all, strong acids. To be classified as a strong acid, an acid has to fully and completely disassociate. Disassociate means it breaks up into its parts and releases all of its hydrogen into the solution. Remember, anybody that starts with the word hydrogen is classified as an acid. So if every one of the hydrogens breaks apart from whatever else it's bonded to, it is considered a strong acid. We also say that's called donating all of its protons to the solution. The reason being is if you are creating a formula, remember when you create a formula, let's take an acid like H2SO4. When you have this sulfuric acid here and it breaks into its parts, it breaks back into H plus 1s and SO4 minus 2s, okay? All of these H plus 1s, as far as science is concerned, are just protons. Let's go back and look at a Bohr model of an H plus 1. So how many protons does a hydrogen have? It just has 1, okay? How many neutrons does a hydrogen have? Well, its mass is only 1, so it doesn't have any neutrons, okay? How many electrons does it have as an atom? Well, 1. How many electrons does it have when it's an H plus 1? That means it gives away its electron. And if it gives away its electron, then all that remains to a hydrogen plus 1 ion is just a proton. So when we have ions of hydrogen, we say it's a proton because that's all that remains in an H plus 1 hydrogen ion is only protons. Okay. Strong acids that disassociate completely donate all of their protons into the solution. Okay, they break up completely. So not all acids are strong acids. There's a small list of strong acids. There are 7 acids on the strong acid list that when they break apart into whatever they are made from, whichever 2 sets of ions that they're made from, when they break apart completely, they're classified as a strong acid. Okay. So the 7 strong acids are perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and chloric acid. Now, of course, you're going to write them down, but I will let you know in past, these are a memorized fact. So if you want to be efficient at solving your problems, you need to know these 7 strong acids by heart. So let's tell you how I memorize them. For starters, I want to point out the fact that all of them are ic acids. What does that do for me? If I see an acid whose name ends in us, I know absolutely it's not on the strong acid list. Okay. The other thing is I have looked at a periodic table of the elements. I'll show you on the slide coming up, and I have found out where these elements are on the periodic table so I can have a visual cue for myself. Then I created a mnemonic tool to memorize them from that. So let's look at the periodic table and I'll talk to you about how to memorize them. So the acids on the strong acid list are nitric acid, which is NO3. Remember, I remember that they're ics, they're not ites. So they're the 8 version of it. So I know it's something with nitrate. So I call this, when I memorize it, NO, for N and with oxygen, NO. Then the next one that I have is SO. It's sulfuric, so it's SO, and remember the orange ones, this is the orange section, of the periodic table. The orange ones are all O4 when they say 8. So those would be the X. So far I have no, so. Then the next one that it is all of the ways that you can have an ending with chlorine. So perchloric, chloric, and hydrochloric. So perchloric is the H with the ClO4. That's an L, not, that's a lowercase L. So perchloric, chloric, and hydrochloric, which means it doesn't have any O's at all because it got to keep the hydro. So I call that clo, or Cl. So I have no, so, clo. Then I say Cl, Br, I, because the Br and the I, just like the HCl, is just an HBr, which is hydrobromic, and an HI, which is hydroiodic. So if you look back on the list that we had, it was no, so, clo, Cl, Br, I. So I kind of sing a Sound of Music song, like the deer, a female deer, ray, a drop of golden sun. I kind of sing it to that tone. So I have no, so, clo, ClBri. So of course the ClBri, I dropped the song on that, but that's how I memorized them. No, so, clo, ClBri. And they're all the ick versions. So that's how I know whether they're O3 or O4, because I already had those memorized. So what would make something a weak acid? You're a weak acid if, oppositely, you don't disassociate completely. You disassociate incompletely. It does not release all of its hydrogens in solution. It only donates part of the protons into the solution. So some of the acid breaks apart into solution and some of them don't. So some of them stay together and some of them do break apart into their components that they make up when they're in solution. So they mostly stay together. If you're a strong base, they disassociate entirely. Again, so strong means completely disassociate, and they break apart into their components that they're made of. So into lithium, which is a +1 ion, and hydroxide, which is a -1 ion. So you'll notice on the periodic table where they're at, it's basically column 1 and most of column 2, just not beryllium or magnesium and not the two guys at the bottom of those columns. And when they're bonded with hydroxide. You're a weak base that does not fully ionize in a solution. So you don't completely break apart, you mostly stay together. All right, so we've got 3 different definitions of acids and bases. So let's start with Lewis's definition. So what do we already know about Lewis? We've talked about Lewis before. What was Lewis known for so far in this class? We know him from what unit? Hopefully you said molecular geometry and Lewis dot structures. So what do the dots represent in a Lewis dot structure? What did the dots represent? Hopefully you know they represented the electrons and the valence energy shells. So those electrons are what Lewis structures are made of. So Lewis is our electron guy. So Lewis's definition are based on electrons because that's what he did his study of, electrons. So what he said was if you're an acid, you are an electron pair acceptor. So acids take in electron pairs. So an acid is an electron pair acceptor. And the way I remember it is I know that Lewis has to do with electrons. And then my association is acids acceptor. The two A's go together. Bases are electron donors. So B and D. So the A's go together, and then B and D, which B and D look very similar, of course, to each other. So both of them, of course, have to do with electrons. So if you remember this part, you just have to remember acid is an acceptor, base is a donor. Base is a donor. Acid, acceptor, base is a donor. And what they're accepting and donating are electron pairs. Okay. The next definition is Bronsted Lowry's definition of an acid and a base. So Bronsted Lowry's definition, according to him, an acid donates a proton. Remember, I already talked about that a hydrogen ion is the same thing as just a proton because it's no electrons, that's how it got a positive charge, and one proton in the nucleus. So Bronsted Lowry's definition is an acid donates protons. So acids donate protons because acids start with the word hydrogen. So formulas for acids have hydrogen as their first name, and they are donating protons because protons is another name for a hydrogen ion. Conversely, they are bases, according to Bronsted Lowry, accept protons. So acids donate protons, they have them to give because they are their first name, and bases take in protons because if you know one direction, then you know the other. So if you remember that Bronsted Lowry, acids donate protons, then you can remember that bases accept protons. It's basically the opposite of Lewis's structure because Bronsted and Lowry are talking about the positive proton, right? And Lewis was talking about the negative electron. So acids accept electrons in Lewis's structure, and acids donate protons because that's the oppositely charged item. So they're really saying the same thing. They're just talking about the different particle. So according to Bronsted Lowry, proton donors are acids, proton acceptors are bases. All right, so in Bronsted Lowry, he does a thing where he has a special word for what they turn into in a reaction, and they are called the conjugate. So this says, what's the conjugate base on the right side? First, to be able to answer this question, which is a very common question, you first have to determine which thing is the acid. Okay. After you determine who is the acid, remember, who gave up hydrogens is the acid. Do watch out for water because water is HOH, which means it's made up of H plus ones, which are the indicator for acids, and OH minus ones, which are the indicator for bases. So water can act as both because it has both the makeup of the acid and a base, hence the reason that water is neutral. It's made up of the compound that makes an acid and the compound that makes a base. So if you are a proton donor, if it donates a hydrogen ion, it's a proton donor. So the first thing is you find out who gave up the proton. That would be who your acid is. Then if you're not the acid, you're the base. Okay. So here's an example. I'll pretend that's a reaction arrow. It didn't format correctly. So when you're looking at the reaction, so this guy could be both, but this guy's an acid, okay? This thing is an acid. How do I know? Look on this side and you can see who donated the hydrogen. I mean, who gave away the hydrogen. You see, here's the piece that's left. So obviously, this thing gave away its hydrogen. If it gave away its hydrogen, it is classified as the acid. If this is the acid, then the other thing is the base. Okay, so if you're not the acid, you're the base. And then the conjugate is the reversed thing on the other side. So the thing that used to be the acid is now called the conjugate base. And the thing that used to be the base that took in a hydrogen is now called the conjugate acid. Because if we flip the reaction and talked about it the other way around, who would be able to give up a hydrogen now? This guy would be, so he would be the acid. So when you're looking at the formula, the first thing you have to look at is find out who is the acid, the other guy's the base. On the flip side of the reaction, whoever used to be the acid is now the conjugate base, and whoever used to be the base is now the conjugate acid. The word conjugate is always associated with the thing that is on the product side. The acid substance becomes the conjugate base, and the base substance becomes the conjugate acid. All right, let's give it a try. So, what can accept a proton? Bases accept a proton, okay? So, look on here and tell me who is the acid and who is the base. That's what you have to figure out first, because the question says, which is the conjugate base? So conjugates, remember, are always going to be on the right side. So it's one of these two things. To figure out who it is, you have to figure out which one of these two things is classified as the acid. Remember, water could be the acid because hydrogen's its first name, but you have to decide by looking at the other thing. If it's an acid, then water is going to play the role of the base. If it's a base, well, then the water could be the acid in that case. So how do I know? Look at its first name. This is hydrogen cyanide. So this thing right here is your acid. If that is your acid, then water's playing the role of the base. Whatever used to be the acid on the other side, see, this is what it gave away its hydrogen. This is now the conjugate base, and that leaves this to be the conjugate acid. Conjugates are always on the product side, the right side of the reaction. Okay, so that one is your conjugate base. That's the answer to your question. Here is a practice sheet to practice over some more of the identifying conjugate acids and bases. So first step, figure out who is your acid, okay? So of course the answers are here, but figure out who is your acid. So that's your acid, makes that your base. That's your conjugate base. That's your conjugate acid. So that's how it would work, okay? So your conjugate base is the ClO2, okay? So your acid becomes your conjugate base. So next one, who is your acid? This is your acid. If this is your acid, this is your base. If this is your acid, whatever it became is now your conjugate base. And whatever used to be the base is now your conjugate acid. So the conjugate base here is your SO4 minus 2. Figure out who is the acid and who is the base. There's no hydrogen on this first thing. He can't be your acid. So water is playing the role of your acid. If water is your acid, then this chloride ion is your base. This makes this your conjugate acid, and this makes this your conjugate base. OH minus 1 is your conjugate base. So I've got HF and H2O. HF is your acid, starts with the word hydrogen. That means H2O is your base. If you used to be the acid, you're the conjugate base. If you used to be the base, you're the conjugate acid. So in this case, fluoride ion is going to be your conjugate base. So figure out who is your acid. This starts with hydrogen. This is your acid. Makes this your base. The thing that used to be your acid is now your conjugate base. The thing that used to be the base is now your conjugate acid. So in this case, the Cl is your conjugate base. All right, our last definition is Arrhenius's definition. And this is basically the definition that we knew when we identified acid-base reactions. Remember, we had double replacement reactions where, so say you had HCl plus NaOH yields NaCl, and remember it said and H2O, because remember H2O is like saying HOH. So remember when we did identifying reactions and we had a double replacement reaction like this where we could identify if you had an acid and a base. That's Arrhenius's definition. Arrhenius says if a substance contributes hydrogen ions into the solution, meaning it starts with the word hydrogen, if it contributes hydrogen ions to the solution, it's an acid. And if it increases the concentration of hydroxides in the solution, then it's a base. So an acid is a substance when dissolved in water increases your hydrogen ions, and a base is a substance that when dissolved in water increases the hydroxide ion concentration. So those are our original definitions, was Arrhenius's. And the way I remember that is A was first. It's the first way we learned how to identify an acid or a base, was Arrhenius's. Okay, so they're going to do some more conjugate acid-base pairs. And the way an acid-base pair differs is by an H+, just one H+. So a conjugate acid-base pair are these that you're going to see here, acid-base pairs. If they differ by one hydrogen, then the answer is yes. Is the difference between OH minus 1 and an H2O a hydrogen? The answer is yes, because HOH is what H2O is. You see, the difference between OH and HOH is one hydrogen. Okay. How about HPO3 with a -2 charge and PO4 with a -3 charge? Is the difference between these two just an H? And the answer is no. This one has also, right here, one more O. So it's not just the difference of an H. This one has an extra oxygen, so it is not a conjugate acid-base pair. Is the difference between these two a hydrogen ion? Remember, a hydrogen ion is an H+1. And the answer is yes. This is 4 H's in an N. This is 3 H's in an N. Why does this have a +1 charge, but this is neutral? Because when you added this extra H+1, it brought along its positive charge with it. Okay, so having an extra H+1 is what makes you an acid-base conjugate pair. Are these acid-base conjugate pairs? Is the only difference between these two things a hydrogen? And the answer is yes. This one has 2 hydrogens. This one only has 1 hydrogen. The difference in the charge, once again, has to do with having an extra H plus, and that got rid of the charge of -1. So an H plus makes you a conjugate pair. How about the difference between SO4 minus 2 and HSO4 minus 1? Yes, the only difference between those is the hydrogen ion with an H plus 1 charge. How about H2SO4 and SO4 with a minus 2 charge? No, they differ by 2 hydrogens, so they're not an acid-base conjugate pair. They don't differ by just 1 hydrogen ion. All right, so let's talk about the difference between being concentrated and dilute. A concentrated solution is one that has a lot of stuff dissolved in a little solvent. So if you put like 5 or 6 heaping teaspoons of sugar in a cup of tea, the sugar in that would be concentrated. If it's dilute, it would be a little bit of stuff in a lot of solvent. Like I just put a teaspoon of sugar in a swimming-sized pool of tea. So be careful. The word strong, oh, I spelled it wrong. The words strong and concentrated are not the same. That's the big thing that people get wrong. Okay, so strong, as far as acids go, means they completely break apart into their pieces. Okay, so a strong acid is one that fully disassociates. It's not talking about what its concentration is, which is talking about how much solvent you have compared to the solute. Okay, so dilute means a little bit of stuff in a lot of solvent. And weak and dilute are not the same thing. Weak has to do with whether or not it fully breaks apart or disassociates in solution. All right, the pH scale. Be careful, don't spell this wrong. Why is that a capital H? Because it's talking about the element hydrogen, which we make capital. Okay, so be careful. That's a lowercase p and a capital H when you write it. All right, so let's talk about the properties of acids. This is how you can identify that you have an acid other than the fact of its formula. Of course, you know you have an acid if its first name is hydrogen. But the other properties associated with acids are they're tart or sour. They are sticky to the feel. They change color in the pH range from red to yellow. So the red, the orange, and the yellow on the pH scale. The pH is between 0 and 6 numerically. So red to yellow, pH 0 to 6. Okay, and they conduct electricity, which are called being electrolytes, but bases do that too. They can be strong or weak, and bases can do that too. So I will tell you that my go-to guy for the, my go-to guy for who is an acid is a lemon. Okay, so I think about a lemon or lemonade. So lemon is my go-to acid. It's sour. If you get lemon juice on your hands or you think about making lemonade, it feels sticky. And lemons are yellow, so it's on the rainbow from the red to the yellow. So that's how I remember the properties of an acid is a lemon. Okay. The properties of a base are they're bitter to the taste, they're slippery to the feel, they change color on the pH from 8 to 14, and they are the blue through purple on the pH universal indicator chart. They also conduct electricity, which is called electrolytes, and they can be weak or strong. Remember, that's based on whether or not they fully disassociate. My go-to guy for a base is soap. So soap is slippery to the feel, and it is bitter tasting, and it doesn't have to be blue, but I already have yellow side is lemon, so I just remember that the soap is the bitter, slippery. All right, so that brings us to the neutralization process. To neutralize something, an acid reacts with a base to produce salt and water. We already had this when we did our double replacement reactions. If you remember, this was our acid-base reaction, and it made a salt. Remember, anything that was left over that wasn't the water was a salt. Okay, so in an acid-base reaction, an acid combines with a base and creates a salt and water. That's called the neutralization process. So we've already did that back in types of reactions, so that should be familiar to you. All right, those are the definitions of acids and bases.